Welcome back to Chapter 20. We are picking up where we left off, so we'll talk a little bit about alternating current versus direct current. Normally, we refer to current as being AC or DC. Direct current, sometimes abbreviated DC, is what you get when the charge only moves in one direction. So that would be like you find in a battery. Batteries are DC current, and predominantly in lab, we'll be using batteries or a power supply that takes alternating current and makes it direct current for us. So if you were going to graph the current as a function of time, over time for DC current, you either have zero or you have your maximum value. You don't have anything in between. If you were looking at the electric potential, the voltage, again, as a function of time, it would either be zero or your maximum value. So direct current is sort of an all or nothing scenario. If we talk about alternating current, our graphic looks a little different. So when we scroll down so we can see it, if you look at it, you'll see that whereas DC current was zero or the maximum value, for AC current, it goes up, it comes down, it goes up, it comes down. What is that all about? Well, AC current or alternating current, the charge moves first in one direction and then in the opposite direction. So this is what happens with things like the electricity we use in our homes, they're AC current. So again, the current positive comes back to zero, goes to negative, back to zero, and then the pattern continues. If you looked at the potential as a function of time, and time's on the horizontal axis on both of these drawings, it does the same thing. It goes up to its maximum and then comes down and up and down. You can see that AC current can be described in terms of a sine function. We're not going to do that. I just wanted to mention it to you. So your current at any point in time is equal to its maximum value times the sine of 2 pi times the frequency of this oscillation multiplied by the time. And you can see you can come up with the same sort of scenario for the voltage. So again, remember, I is current measured in amps, V is the voltage or the electric potential measured in volts. But that does lead us to a new term, and that would be peak current and peak voltage. These have the subscript 0 on them. So I sub 0 is the peak current, V sub 0 is the peak voltage. It's the maximum amount that you can have. In the United States, we've already said that AC current oscillates. In the US, it oscillates at a frequency of 60 hertz or 60 cycles per second. That is not the same all over the world. Different countries have different oscillation rates. So just all electronic devices don't work uniformly the same around the world. All righty, moving along. So when we're dealing with things, because current, you plug something into the wall, it's going to oscillate. The average current would be 0 over a complete cycle. What went up came down and it would average out to 0. So what we do is we use something called the RMS value or the root mean square value. Remember, peak current is the maximum you can have, but the effective value or the line value, the effective value or the line value are two other names for the RMS or root mean squared. So this one term, IRMS, can be called the RMS value, it can be called the effective value, or it can be called the line value. I sub 0 is always just the peak. It has a single name. So the RMS current is equal to the peak divided by the square root of 2. The RMS voltage is equal to the peak voltage divided by the square root of 2. And power is just current times voltage. So P equals IV. So if they ask for the effective value or the line value, that's just the same as the RMS. If they ask for the peak value, that's with the subscript 0 in it. Okay, let's do a simple calculation. Suppose we have a 50-watt light bulb and we're going to plug it into a 110-volt outlet, and we want to know what is the resistance of the bulb. So we know that 50 watts is equal to the power. So P equals 50 watts. It's plugged into a 110-volt outlet, so V is 110 volts. We're trying to find R. And we have two formulas, P equals IV and V equals IR. So to find the R, we could write down V equals IR. We know V, but we don't know I and we don't know R, so that's not going to be helpful. So we must have to start with the P equals IV equation. So P equals IV, so 50 volts equals I multiplied by 50 watts equals I multiplied by 110 volts. Divide both sides by the 110 and you get that the current is equal to 0.45 amps, 0.45 amps. Now that we have the current and the voltage, we can find the resistance. So step 1 was to find the current. Step 2 is to find the resistance. You have V equals IR, so 110 volts is equal to 0.45 amps multiplied by R. Divide both sides by 0.45, and we get that the resistance is 244.44 ohms. Suppose they want to know the RMS value. They give you the line value. They give us the RMS value of 220 volts, and they want to know what is the peak voltage. Well, that's pretty easy. They gave us VRMS. We are looking for V sub 0. Remember, peak only has one thing to keep up with, that's the sub 0. So VRMS is equal to V0 divided by the square root of 2. So our calculation picks up right here. So VRMS is equal to V0 over the square root of 2. So 220 volts is equal to V0 divided by the square root of 2. So V0 is 311.127 volts. Again, the hard part is remembering that RMS and line and effective are all the same thing. And peak is the only one that has the sub-zero. All right, so a couple of problems to try for homework. And then there are obviously some in the study guide. Let's talk about household circuits. So in your house, you have 3 wires that come into the house. If you look at a power line sometime, there'll be 3 wires. One of them is the plus 110 volt line, the other is the minus 110, and the third one is the ground wire or the 0 volts. To get 220 volts, you'd go across both of the 110s. To get 110, you'd either use 0 and the plus 110 or 0 and the minus 110. And remember that plus and minus 110, it's not constant. It oscillates. So it goes positive, negative, at 60 cycles per second, 60 hertz. So we've said that the 0 volt is the ground wire, and it is actually in homes connected to the earth at some point in time. It's connected. Sometimes you can see it in an older home. If you have buried power lines, you don't even notice it's there. So houses are usually wired in parallel, not in series. We talked about series and parallel circuits back about capacitors. So why would you wire a house in parallel? It would use up a whole lot more wire. Well, the reason is if you did it in series, first of all, every single appliance in your whole house would have to be on all the time for anything in your house to work. In series, the current has to go from one appliance to the next appliance to the next appliance and then back to the power supply in order for anything to work. If it's in parallel, you have alternate paths available. So one appliance could be turned off and the others could work in a parallel circuit. So that's one reason. Another is that if you wire it in series, you have a tremendous buildup of heat energy because of the total resistance. When current flows through a wire, it heats up. And if the wire becomes too hot, it can melt the insulation and cause a fire. And that's one of the reasons why you have a circuit breaker or a fuse. If you live in a really old house, like I do, we still have fuses. I keep thinking one day I should have us upgraded breaker box, but I haven't done it yet. So what a fuse or a circuit breaker will do is it disconnects the power supply from the appliance if the sensor, if the breaker or the fuse senses that the temperature has gotten too high and it is dangerous and might cause a fire. So you always want your breaker or your fuse to go between the power supply and the appliance, the device. So we have a little diagram. Remember, this is the battery. These squiggly lines represent resistors. You could think of them as appliances, as maybe a radio, a light bulb, and a microwave. And I'm giving them values of 5 ohms, 10 ohms, and 15 ohms. This is just arbitrary. And we wired it in parallel. The electricity comes from the battery and it splits and goes down through all 3 resistors and then comes back together and goes back to the battery. The breaker has to go between the power supply, so that's this 100-volt battery, and the appliance. So the ideal place for it would be at location A in my drawing, because every other spot I put it in, the electricity has an alternate path. It has an alternate path. So it needs to go between the power supply and the appliances. Breakers are really better than fuses because a breaker can't be changed except by an electrician to a larger size. Fuses screw in like light bulbs screw in, and you can take a 15 amp fuse and replace it with a 20 amp fuse to keep from having to have the fuse burn out. Unfortunately, it's also a fire hazard if you do that. All right, let's look at an example of why we care how big the fuse is. So suppose we have a 15 amp fuse or breaker connected to a room that has a 1200 watt hair dryer, a 1500 watt iron, and 3 100 watt light bulbs, and they're all on the same circuit. If you've ever had to flip a breaker in your home, you might have noticed that maybe the living room is on one breaker or all the overhead lights are on a single breaker. Some appliances get their own individual breaker, like the stove or the clothes dryer, but a lot of times all the outlets in a room will be on a single breaker. So it can be easy to overload the line. So we know that the maximum amount of current you can have is 15 amps. And suppose we allocate these 3 things, the hair dryer, the iron, and the light bulbs, and call them P1, P2, and P3 for the power that they use. So 1200 watts, 1500 watts, and we'll add the 3 light bulbs up to make 300 watts. Maybe they're in a single overhead light fixture. We know that they didn't tell us, I should have, that the maximum amount of electric potential or the voltage that we have available is 120 volts. And so to find out if the fuse is going to blow, we can answer one of 2 questions. We can either say, is the current, the maximum current available greater than or equal to what we use, or is the power greater than or equal to? And we end up only needing P equals IV as our equation. So what I'm going to start with is find out how much total power we're using. So 1200 watts plus 1500 watts plus 300 gives us 3000 watts. This is what we use. So let's see what's available. The maximum we have available is the current times the voltage, so 15 amps, that's the size of our breaker or our fuse, times the 120 volts, that's determined by what the power company sends us, gives us 1800 watts. That means for this 15 amp fuse, that is all the power we've got at our disposal. And we are trying with a 3000 watt total to use way more than that. In order to just barely make it work, you would have to unplug the 1200 watt appliance. To give yourself a little cushion, you could unplug the 1500 watt appliance. So our fuse would blow in this instance, and we'd be sad. If it's a breaker, you just unplug something and go back and flip the breaker. Let's talk a little bit about electric safety. So everybody has seen a three-prong plug. Three-prong plugs have a round wire, that's the case to ground wire, and they have two vertical flat wires. Typically, one of them is a little bigger than the other. I've exaggerated it in this drawing. The smaller of the two is called the hot wire, and the larger of the two is the neutral wire. I wouldn't touch either one if the appliance is plugged in. Don't do it. So what does the case to ground wire do? It connects the case of your appliance to an actual physical grounding wire inside the outlet. And it's there to protect you from electric shock in case the appliance has a loose wire inside of it and it becomes dangerous. Electricity wants to follow the path of least resistance, and the case to ground wire will always have a lower resistance than you do. In fact, I forgot my demo. I might have to do it I'll do it in class. So here's a little professional sketch of a three-prong plug. Again, the round wire is the case to ground wire, and you have a hot wire and a neutral wire. Sometimes in houses you have what are called ground fault interrupters. A ground fault interrupter is an outlet that's used where there's a potential for you to have wet hands, so kitchens and bathrooms, or if you have it outside near a swimming pool. And outside near a swimming pool is a really bad place for an electrical outlet to be. But typically you see ground fault interrupter outlets in kitchens and bathrooms. They look funny because in the middle of the outlet, you'll see a little button. And sometimes you'll go to plug in your hair dryer and it won't work, and you have to press the reset little button. These ground fault interrupters have built-in circuit breakers. And if the outlet senses a different amount of current going into the appliance than comes out of the appliance when you plug it in, it makes a decision to trip the breaker, to pop the breaker, because it says, okay, electricity is going somewhere, not just through the appliance. And the worry, of course, is that the electricity is going through you and you'll get an electric shock. And around water, it's particularly dangerous. In class, we'll have to do a demo of your electrical resistance as a function of, are your hands wet or dry or salty? So let's talk a little about electric shock. About 1% of all accidental deaths are due to some sort of electrocution. Whether you get a severe shock or a very mild shock or almost no shock depends on three things, really. The magnitude of the electric current, the time it spends in your body, and the part of your body that the current passes through. So electricity going from my thumb to my little finger wouldn't be so dangerous as it would electricity going across my heart. If it went from my little toe to my big toe on a single foot, wouldn't be so bad, but I wouldn't want it going through my brain, for example. So electric shock can burn tissue or it can damage organs, and it is something to be avoided. So we want to remember Ohm's law, V equals IR. The V depends on the source of the electricity, the R depends on U, and those two things will determine the amount of current. If you have a really high resistance, then you'll have low current coming through you. So the idea is we want to keep your resistance high. The resistance in a human body varies quite a bit. Whoops, I overshot again. It might go from anywhere from 10,000 ohms to 200,000 or more ohms. In class, we'll do these three. We'll have a meter and measure my hand-to-hand resistance with a dry hand, wet hands, and a salty hand. And I will tell you now, dry hand-to-hand, I guess we could make this dry. We'll have the highest resistance. Wet will be our medium value. And if I can add a little salt to it, that'll be the smallest resistance. So dry is going to be the highest resistance, wet will be medium, and salty will be the smallest. So you don't ever want to have wet, salty hands and be anywhere near electricity if you can help it. One of the reasons they tell you to get out of the water if there are storm clouds, you shouldn't be in the pool or near the pool or wet and near the pool. You shouldn't stand under a tree in a thunderstorm thinking the tree will protect you. It's just going to make you a really good conductor of electricity. So a little general chart, there's some, depending on where you look it up, these numbers might vary. But if the amount of current going through your body is 0.001 amp, so 1/1000th of an amp, you're going to feel a little tingly pain. It won't really hurt too much, but you'll notice it. If you get up to 100th of an amp, 0.01, there will be enough current passing through your body that your muscles will contract and you won't be able to let go. If you go up to 0.07 amps, you'll be in ventricular fibrillation. And with that, your heart is going to beat, but in an erratic pattern, which is not good for you. If you get up to 0.1 amps, your heart is going to stop and won't restart after the current stops. Anything from 1 to 2 amps, you'd have respiratory paralysis. 3 amps would give you severe shock and burns, and anything from 1 to 10, again, sustained contractions of the heart, and you're not going to recover from it. So the bottom line is don't get an electric shock. It can be unpleasant. Defibrillators apply a really brief high current to the heart, and the notion is it starts fibrillating so that it stops that irregular pattern, and once the current is discontinued, hopefully your heart's going to resume beating normally. Hopefully it'll start beating normally. Most large buildings these days have AEDs around. There's one in the science building. Usually most buildings on our campus have an AED. If you see someone in cardiac distress and you feel like they need to have the AED utilized, even if you have never used one, they are self-educating. You don't hesitate after you've called 911 to go ahead and go and break out the equipment and attempt to save somebody's life. I've been educated on 3 different kinds of AEDs, and in the end, they're foolproof. Yes, it's nice to have an expert, but even a non-expert can follow the diagrams and listen to the words and follow the directions. So they're really easy to use. And again, you could save somebody's life that way. If you have some sort of electric shock, administered to you unintentionally. AC is always more dangerous than DC. AC tries to drive your heart at 60 hertz, which would be the same as 3,600 beats a minute, which is of course way too fast. Your heart doesn't want to beat that fast. DC holds the heart in an extended contraction, and sometimes you can recover from that extended contraction. AC is really dangerous, and again, avoid all electric shock if you can. If you do experience an electric shock or see someone who has, certainly call for help, 911. Turn off the power at the main breaker if you know how. And if the power can be turned off and they're not still electrically dangerous, then you can use CPR, but don't touch someone if they're holding a live wire. You don't want to be the second casualty in the list. So let's talk a little bit about how sometimes items can be okay on a power line and sometimes they can't. So my drawing is incorrect. There should have been a third wire. I was going to draw one in and I didn't. I apologize. If you wanted to sketch in the third wire, which should go from post to post. I wonder if I can do that. Shapes, align, yes. We're going to go ahead and draw in my, round wire. Right there. Okay, so we've got my third wire. I was just worried that there were only two of them. We have the third wire. A bird can sit on the wire and not get an electric shock because both of his feet are on the same power line. So remember, V equals IR. So maybe the power line is a 10,000 volt line, but guess what? 10,000 volts coming through one foot and 10,000 volts going through the other foot. Delta V, the change in voltage, well, 10,000 minus 10,000 gives you 0. So the bird experiences 0 voltage, so that means there's 0 current passing through him. Now, suppose you are down on the ground and you've got some stick, and you, like an idiot, want to touch the power line with your stick. Well, the power line's at 10,000 volts, and that didn't hurt the bird, but guess what? Your feet are not on the power line, your feet are on the ground. And the voltage of the ground is 0. So power line at 10,000, feet at 0. 10,000 minus 0 means you have 10,000 volts going through you. You are going to be a sad person. All right. When I was in graduate school, one of the guys said when he was in middle school, they would throw sticks onto the power lines and get a stick that was long enough to go across the one high voltage line and the middle line, which is the ground wire. And when they would do that, if there were any birds on the wire or squirrels on the wire, it would fry them because, again, the wire then gets grounded because they connected the 0 volt line to it. So we definitely don't want to ground out, just like you don't want your feet on the ground. Oh, there's all kinds of examples of how you can inadvertently die because you were careless around power lines. In Alabama, when I was in graduate school there was a story about a sailboat had a metal mast, and it was found a few days later with the occupants of the boat dead, and they had been electrocuted. What had happened is they had sailed in such a way that their metal mast had come in contact with some sort of power line, and it had electrocuted them. And again, while I was in Alabama, there was a guy on horseback, and he had a stick, and he was just touching all kinds of things, and he touched a power line, and of course ground it out. And every time I tell that story, someone wants to know what happened to the horse, and you know, I don't know. I would love to say the horse survived and the dumb rider didn't, but I don't have a clue. So dead branch to lift a live wire. There was a story a few years back here in North Carolina about a Duke Energy worker who had gone out, a live power line had been, downed line had been reported. And he decided to just pick up a stick on the side of the road to move it out of the way. Unfortunately, the stick conducted electricity well enough that the minute he touched the live wire with it, he too was a dead power company employer. Parachute on a power line, well, that's kind of like the bird. As long as the parachute and you are only on a single power line, you're safe. But if you have the parachute and it drops down and touches the ground, you'll get electrocuted. If your friend comes up in his pickup truck to try to help you, the minute he touches you, you'll both get electrocuted. So be careful around power lines. And we will stop the video